We've all seen the amazing things large language models can do lately.
Yeah, they're everywhere.
They generate text, hold surprisingly coherent conversations, summarize huge amounts of information. It really feels like magic sometimes, doesn't it?
It truly does. They've certainly captured the world's attention.
But, if you've played around with them much, you pretty quickly bump into their limits.
Mm-hmm.
They have these blind spots, these knowledge gaps. Ask one who won a specific award next year. Or, say, about proprietary data specific to your company.
And they just won't know.
Right.
That's the fundamental challenge, isn't it? They're limited by their training data.
Which had a cutoff date.
Exactly. And it definitely doesn't include your latest sales reports or, internal research docs.
And sometimes when they don't know, they don't just say, I don't know.
Yeah.
Well, they confidently make things up.
That's the dreaded hallucination we hear so much about.
Yeah.
And it often comes from that training data being just so vast, but also sometimes contradictory or, simply outdated.
So how do you take these incredibly powerful models, which are sometimes, uninformed or stuck in the past,
right,
and communicate with them effectively? How do you ensure they give you accurate, up-to-date, domain-specific responses?
Instead of just plausible sounding fiction.
Exactly.
Yeah, it's definitely more involved than just typing a simple question and, hoping for the best.
This is where some critical techniques come into play.
Absolutely. And that's really what this deep dive is all about today. We're going to unpack the key methods used to enhance LLMs.
Thinking particularly about prompt engineering and Retrieval-Augmented Generation, or RAG.
Precisely, Argyle. We'll be drawing insights from the sources you've shared with us.
Okay, so our mission here is basically to give you a shortcut to understanding what these techniques are.
How they work, their strengths, weaknesses.
And, importantly, how they're evolving.
Yeah.
The goal is really to show you how to make LLMs truly practical, reliable tools.
Grounded in reality, not just fun chatbots.
Right. Let's dive in. So, kicking us off, let's talk about the starting point. Prompt engineering. What is it at its core?
Well, at its most basic level, prompt engineering is about strategically designing the input you give to an LLM.
The prompt itself.
Exactly, the prompt. Designing it to get the output you actually want. Think of it as the art and science of writing effective instructions for the model.
So it's essentially mastering communication with this particular type of AI.
Precisely. And it's vital because, like we said, LLMs can hallucinate or just give really generic answers.
Right.
They have billions of facts and patterns kind of baked into their training data, but the prompt is what directs their attention.
Okay, but how does just changing the words actually direct the model? What's happening under the hood?
Well, when a model processes a prompt, it's using these complex attention mechanisms to figure out what's important.
Okay.
So by including specific elements in your prompt, like, say, examples of the answer format you want, or adding relevant context, or giving explicit step-by-step instructions,
You're sort of guiding it.
you're activating specific pathways and patterns the model learned during its training. You're essentially making its existing capabilities available for your specific task.
So the key insight here is you're not adding new knowledge with prompt engineering.
No, not at all.
You're just getting better at activating and directing the knowledge and abilities already logged inside.
That's exactly it. There's a great analogy in the sources about telling a model to think step by step. This doesn't actually teach it logic from scratch. What it does is activate reasoning patterns it learned from seeing countless examples in its training data where, methodical steps led to accurate results.
And the benefit of this sounds like it's pretty immediate and accessible.
Oh, absolutely. The big plus is there are no back-end infrastructure changes needed. You just change the prompt, run it again.
Anyone can do it.
Pretty much anyone using an LLM.
But the limitation then becomes pretty clear, right? You're confined to whatever the model already knows.
Exactly, or is capable of, based on its training data.
You can't teach it something it doesn't know, or update information that's become outdated since training.
That's the fundamental ceiling for pure prompt engineering. No matter how clever your prompt is, you can't make the model recall information it was never trained on.
Or learn about events that happened last week?
Correct. And yeah, it often involves a fair amount of trial and error to find the most effective wording. It's definitely still, an art as much as a science.
Okay, so prompt engineering is powerful for getting the most out of the model's existing capabilities, its internal knowledge.
Right.
But what if you need the model to know things it simply doesn't have, like proprietary company documents or breaking news?
That's precisely where Retrieval-Augmented Generation, or airy steps onto the stage.
Okay.
The core idea here is to combine the LLM's broad general knowledge, the stuff from its training, with specific external information that you provide.
Right, information that you control.
Exactly. That could be your private data, up-to-date web content, curated documents, you name it.
So it's about giving the model access to a knowledge base beyond its original training.
Precisely. The main purpose is to make LLMs more accurate and, crucially, more current.
By grounding them.
Yes, by grounding their responses in specific, trusted sources you control or select. This is a key way to prevent hallucination when dealing with specific facts.
And it allows for citations too, I imagine.
Absolutely. That's a huge benefit. It can provide citations or references for its answers.
So the process isn't just, my question goes straight to the LM, it gives an answer.
No, there's a critical intermediate step.
Okay.
That's the core difference. The flow changes significantly. Instead of just prompts LLM answer with a RAG, it's more like prompt and/or retrieve relevant content from your designated knowledge base.
Okay, retrieve first.
Then not, combine that retrieved content with the original prompt, send that expanded input to the LLM.
Ah, so the LLM sees the question and the relevant facts.
Right, and then the LLM generates an answer based specifically on the retrieved content. That's like asking someone a question, but first handing them the specific articles or notes they need to reference before they formulate their answer.
That's a perfect analogy. You're giving the model the specific facts it needs right in the moment it needs them to formulate a correct answer.
The sources gave that really clear example with company earnings.
Yes, that's a good one. If you ask a general LLM about, say, a company's total earnings for a specific year, it might give you an outdated number from its training.
Or just make one up.
Or even hallucinate one, yeah. Confidently stating $19.5 billion perhaps.
Okay.
But using ARA connected to your company's actual financial database, the system would first retrieve the document chunk with the correct figure. Let's say it's $5.4 billion.
Right.
It then feeds that figure, that fact, into the LLM's context along with the question. The LLM is now grounded by that $5.4 billion fact.
And it will use that number to answer accurately.
Exactly, because it's referencing a trusted specific source that wasn't necessarily part of its original broad training. It leverages the model's ability to process information and generate text.
But ensures it's using factual data you provide.
Okay, so RAG retrieves information from a knowledge base. The sources really emphasized that a key player for many types of data in RAG is something called a vector database.
Ah, yes, vector databases. They're crucial.
What exactly are these?
They're a specialized type of database. They're designed specifically to store and query numerical representations of data.
These vector embeddings they mentioned.
Exactly, vector embeddings.
That sounds a bit abstract. We're turning data into lists of numbers.
Essentially, yes. Think of them as long lists or arrays of numbers. These numbers are created by sophisticated models called embedding models.
Okay.
There are models for text, images, audio, trained on massive data sets. These models learn to capture the semantic essence, the meaning, the key characteristics of complex objects.
And represent them as points in some kind of high-dimensional space.
That's the transformation. You're taking text, pictures, sounds, and converting them into, well, math, into vectors. And the really surprising bit, the kind of magic here, is that in this high-dimensional vector space, items with similar meaning or content end up being positioned close together numerically.
And dissimilar items are far apart.
Exactly. An embedding for a document about, say, machine learning algorithms will be mathematically close to an embedding for neural network architectures, but far, far away from one about Renaissance art.
Okay, that's the key. Similarity means closeness in this number space. So how does RAG use this for my documents, my PDFs and Word files?
So you take your domain documents, your Word files, PDFs, wikis, emails, whatever. You first break them down into smaller, manageable chunks.
Right, chunking.
Then each chunk is converted into a vector embedding using one of these embedding models.
Okay.
And these embeddings, along with a link back to the original document chunk, are stored in the vector database. This essentially creates a searchable numerical index of your entire knowledge base.
And when I ask a question, how does it find the right chunk?
Your natural language question is also converted into a vector embedding, critically using the same embedding model used for the documents.
Consistency is key there.
Absolutely. Then the vector database performs a similarity search. It looks for the vector embeddings and thus the document chunks that are mathematically closest in that vector space to your question's embedding.
So it finds the pieces of text that are semantically most similar to my question.
Precisely. These closest vectors represent the pieces of your knowledge base most likely to contain the answer.
That makes sense for a small database, but what about, millions or billions of document chunks? Comparing my questions vector to every single one sounds incredibly slow.
Ah, yes, that's where vector indexing comes in. It's crucial for performance at scale.
Okay.
Techniques using algorithms, often called approximate nearest neighbor, or ANN, algorithms are used.
Approximate.
Yeah, instead of checking every single vector for a perfect similarity, which is too slow, they quickly find vectors that are highly likely to be among the closest matches.
So you trade a tiny bit of potential accuracy for speed.
Exactly. You accept a tiny potential trade-off in finding the absolute single closest document for a massive gain in speed. This is essential for making RAG queries work in real time.
So vector databases provide the flexibility for different data types, scalability for huge amounts of data, and speed through this optimized indexing and querying.
They really are the engine for the retrieval step in RAG.
Got it. Let's walk through the complete basic RAG workflow we saw in the sources then. It sounds like there are two main phases, right? An offline part and an online part.
Yes, that's a good way to think about it. An offline phase and an online phase.
Okay, tell me about the offline phase first. Setting things up.
Right. In the offline phase, this is where you prepare your knowledge base. You start with your raw documents, PDFs, reports, notes, whatever holds your domain knowledge.
Your source material.
Exactly. You break these large documents into smaller, manageable chunks.
Chunking again.
Then, using an embedding model, you create that unique vector embedding for each chunk. These embeddings, along with metadata, maybe the source file name, page number, and pointers back to the original source document chunks, are stored in your vector database.
Creating the index.
Yes, this process is sometimes called indexing or ingestion. It builds the searchable index of your knowledge. It's the prep work.
That's setting up the system. What happens in the online phase then? When a user actually asks a question.
This is the dynamic part happening in real time. The user's question comes in.
Okay.
A component, often called the RGay retriever, takes that question and converts it into a vector using the exact same embedding model used during the offline phase.
That consistency thing again, very important.
Absolutely critical for the similarity search to work properly. The retriever then performs that similarity search in the vector database.
Looking for the closest matches.
To find the top K most relevant document chunks, K might be 3 or 5 or 10 passages, depending on how you configure it.
So it finds the few pieces of information most likely to contain the answer.
Right. These retrieved chunks are then taken and strategically placed into the LLM's context window.
Alongside the original question.
Exactly. The LLM doesn't just see your question in isolation. It sees your question plus these relevant factual passages retrieved from your knowledge base.
And then the LLM generates its answer.
Yes. And this is why RG is so powerful. The LLM is instructed, usually via the system prompt, to generate its answer grounded in the provided context.
Using the facts you just gave it.
Exactly. Using the facts from your knowledge base.
And that's why it's more accurate and less likely to hallucinate on specific or new information. It's using your facts, not just guessing based on its broad, sometimes old, training.
Precisely. It dramatically improves accuracy, especially for domain-specific or recent information. And a key benefit we touched on, the model is now equipped to potentially say, I don't have enough information in the provided context to answer that.
Which is much better than making something up.
Much, much better.
And the sources pointed out this modularity. You can swap out the vector database or the embedding model or even the LLM itself.
Yes, that modular design is a major advantage. It gives you flexibility and makes upgrades easier down the line without rebuilding the whole system.
Okay, but a potential weak link seems to be that retriever step.
Yes.
If the system fails to find the truly relevant documents, even if they exist in the knowledge base,
Then the LLM is left without the facts it needs.
and the answer will be poor, or it might fall back to hallucination.
That's a critical point. The quality of the final RAG output is highly dependent on the effectiveness of that retriever. A poor retrieval step means the LLM doesn't get the necessary grounding and the answer quality suffers significantly.
So improving retrieval must be a big focus.
Absolutely. A lot of current research and development is focused squarely on improving that retrieval process.
Okay, so basic RAG adds external knowledge.
Yeah.
But the sources also showed how you can layer other prompt engineering techniques on top of RAG to refine the interaction even further, right?
That's right. While RAG gives the LLM the information, these other techniques help refine how the LLM processes that information or reasons with it, or extracts specific details from it.
like chain of thought, SUOT. That seemed useful for more complex tasks.
Yes, chain of thought is about guiding the LLM to break down a complex problem into smaller logical steps before arriving at the final answer.
So like explicitly telling the LLM how to approach a problem step by step, almost like you'd explain solving a math problem methodically.
Exactly that. The prompt includes instructions or maybe examples that encourage this step-by-step internal reasoning process.
Make the thinking clearer.
It makes the LLM's conclusion more transparent and often more accurate, especially for multi-step tasks. The sources suggested it's often most powerful after you've grounded the model with relevant facts via ARI.
Okay, so first, give it the ingredients, the facts via a RIDE.
Right?
Then give it the recipe, the steps via SUOT.
That's a great way to put it.
And react. That was reasoning plus action. That sounded like it involved more interaction with the outside world.
It does. React is a technique where the LLM goes through a kind of loop. Thought, action, and observation.
Thought, action, observation. Okay.
The action part often involves interacting with external tools or resources, things like performing a web search, maybe querying a different database, or even using a calculator.
So RAC is great for accessing your specific knowledge base, but React lets the model go out and find public information, or maybe real-time data.
Precisely. The model thinks about what information is needed. It decides on an action, like a web search for recent data. It then observes the result of that action, like the search results.
And uses that?
And uses that observation to inform its next thought and maybe another action, or to finally generate the response.
So like that example of needing financial earnings for both, say, 2022, which might be in your RAG data.
Right.
And maybe 2024, which might only be publicly available online.
Exactly. React would let the model use your private data and go search the web for the latest figure to provide a complete, non-hallucinated answer.
Combining internal reasoning with external information gathering. Makes sense.
Yeah, it's quite powerful for those kinds of mixed knowledge tasks.
And what about direct specific prompting, DSP? That sounded simpler, but still effective.
It is simpler, but very useful. DSP basically uses specific formatting or clear hints within the prompt to encourage the LLM to extract particular values or specific pieces of information.
From the text it's processing, or even from the answer it's generating.
Both, potentially. It's like giving a hint in a game, to get someone to focus on a specific detail you want them to find.
Okay.
You might ask a general question about a document you retrieved via RAG, but then use DSP to say, now, from that information, specifically pull out the project name and the completion date.
Just focusing as output.
Exactly. It helps focus the LLM's output on the precise data points you actually need.
So these techniques really work together, don't they? RA brings in the relevant facts.
The ground.
And then techniques like COTI, React, and DSP help the LLM process, reason about, and extract information from those facts in a much more structured and targeted way.
That's the power of combining them. You build layers of capability.
It sounds like even basic RAG is pretty transformative, but the sources made it really clear that the RAG landscape isn't static. Not at all.
Oh, definitely not. It's an extremely active area of research and development. That core flow we discussed, indexing retrieval generation, is being enhanced in some pretty clever ways.
So what are some of the ways people are improving that initial retrieval step, getting better documents in the first place?
A major focus is on improving query translation or query transformation.
Changing the user's question.
Essentially, yes. Modifying the user's original question before it's used to search the vector database. The aim is to improve the relevance of the results you get back.
But why change the user's question? Isn't that what they want answered?
Well, sometimes the way a user phrases a question isn't actually the most effective way to find the relevant documents in a semantic search system.
Yeah.
So techniques like multi-query or RAG fusion take the original question and automatically rephrase it into several different versions or perspectives.
Like asking in multiple ways.
Exactly. Then they perform independent searches for each of those rephrased queries and combine the results, often using a smart ranking method.
It's like trying a few different keys in the lock to make sure you open the right door. A sort of shotgun approach.
That's a good analogy, yeah. A shotgun approach to retrieval to increase the chances of hitting the right documents. Reliability goes up.
What else?
Other methods include decomposition, where you break a complex multi-part question into simpler sub-questions.
Handle them one by one?
Potentially, yes, or there's step-back prompting. This is interesting. It asks the LLM to generate a more abstract, higher-level conceptual question that kind of underlies the user's specific query.
Okay. Right.
Then it retrieves documents relevant to both the original question and the step-back, more conceptual question. The idea is to capture foundational concepts that might be key to answering the specific question well, especially in technical domains.
That's clever. And HIDE, hypothetical document embedding. That name is intriguing.
HIDE is a really neat one. It actually gets the LLM to generate a hypothetical answer or document to the user's question first.
It writes a possible answer before searching.
Yes. Then it creates a vector embedding of this hypothetical answer, not the original question. And it uses that embedding for the similarity search in the vector database.
Why would that work better?
The intuition is that the embedding of a potential answer might be semantically closer to the relevant source documents than the embedding of the original question, which might be short or maybe poorly worded. It leverages the LLM's generation ability to improve the search query itself.
So those techniques improve what you search with.
Yeah.
What about improving where you search, especially if you have different kinds of data sources?
That leads directly into routing. Routing is all about intelligently deciding which knowledge source or tool is best suited to answer a given question.
Because you might not just have a vector store.
Exactly. You might have data in a vector store, but also critical info in a traditional relational database like SQL, maybe a graph database, or you might even need to use web search or just fall back to the LLM's own general knowledge for some queries.
So the system figures out the best place to go look for the answer, like a dispatcher.
Pretty much. This can be done with logical routing, where an LLM analyzes the question and metadata about your sources to make a decision. Or semantic routing, where the question's embedding is compared to embeddings that represent the content or purpose of each available source, and it picks the closest match.
And for those sources that aren't vector databases, like traditional SQL databases, how does RAG interact with them? Does it just pull whole tables?
No, that often involves query construction. Many databases require structured queries, SQL for relational databases, maybe Cipher for graph databases.
Very specific languages.
So query construction uses an LLM, often one with good function calling or structured output capabilities, to translate the user's natural language question into the correct query language and format for that specific target database. It needs to follow the database's schema.
So turning my plain English question like, find all customers in California who spent over $1,000 last year,
into the actual SQL query needed to get that information from your customer database.
Okay. The LLM acts as a translator.
Exactly. Between the user's request and the database's required language. This makes RAG much more versatile, allowing it to pull information from all sorts of structured data sources, not just unstructured text in vector stores.
We talked about indexing documents into the vector database earlier. Are there more advanced ways to do that part two, beyond simple chunking?
Oh, yes. Advanced indexing techniques aim to improve how documents are processed and stored to make retrieval more effective, especially for complex or very long documents.
Like what?
One approach is multi-representation indexing. Here, you index not just the original document chunks, but also different representations of them.
Like summaries.
Exactly, like summaries, or maybe just titles or abstracts. This allows you to potentially search a summary index first, to quickly identify potentially relevant documents, and then retrieve the full text of only those specific documents rather than just small chunks. Useful for finding whole relevant articles.
And hierarchical indexing.
Correct. Techniques like hierarchical indexing organize document chunks into clusters, maybe based on topic, and then create representations, perhaps summaries again, of those clusters.
Why group them?
This helps for questions that require synthesizing information across many different chunks or even across multiple documents. It helps the system navigate very long source texts or knowledge bases more effectively.
Okay, that makes sense. And finally, this idea of active RAG or agentic RAG. This sounds like the LLM is really taking charge now.
This is a significant evolution, yeah. Here, the LLM acts much more like an agent within the RAG workflow itself.
Not just generating text at the end.
No, it's not just a passive recipient of context anymore. It's making decisions, it's evaluating information, and it's determining the next steps in the process.
So the LLM is actually thinking about how to get the best answer and deciding if the information it found is actually any good.
Precisely. The core idea is to introduce evaluation and corrective loops into the workflow. So in workflows described as self-RAG or adaptive RAG, the system might retrieve documents.
Okay.
Then use the LLM itself to grade how relevant or helpful those retrieved documents actually are for the question asked.
The LLM grades the search results.
Yes. And based on that grade, there's a decision point. If the documents are good, great, proceed to generate the answer. But if they're poor, or maybe ambiguous,
Then what?
the LLM might decide to take a corrective action. Like, it might decide to rewrite the original query and try the retrieval again.
Try searching differently.
Or it might decide it needs to do a web search instead, or maybe query a different database. Or it might even conclude, I can't answer this question reliably with the information available.
So the LLM is dynamically controlling the whole process based on the quality it's seeing.
Yes. The LLM is used not just for the final text generation, but also potentially for deciding which data source to use, evaluating the quality of the retrieved content, maybe even evaluating the quality of the answer it generated itself.
Checking its own work.
And deciding on the next step in a potentially multi-stage process. This makes RG systems much more robust, more adaptable, and less brittle.
Especially for complex questions or maybe slightly out-of-domain queries.
Exactly. They can handle failures more gracefully. Frameworks like LangGraph are emerging specifically to help build these more complex, agentic workflows with defined steps, states, and transitions.
That sounds incredibly powerful. Really moving towards creating more reliable and, well, sophisticated knowledge assistants.
That's absolutely the goal, making the RAG system more intelligent about how it finds and uses information, not just what information it uses.
Okay, so R, in all its forms, is all about retrieving information from a knowledge base to ground the LLM. But the sources also presented a different strategy for augmenting LLM knowledge, CAG, Cache-Augmented Generation.
Yes, CAG. It takes a fundamentally different approach than ARGA.
How so?
Instead of dynamically retrieving small, relevant chunks on demand like RAG does, the core idea of CAG is to preload a significant portion, maybe even the entire relevant knowledge base as long as it fits.
This where?
Into the LLM's context window. You load it directly into the model's internal memory, specifically what's called the KV cache, in a single step before you even start asking questions.
Okay, let me make sure I get this. RAG finds the relevant pieces when you ask the question.
Right, just-in-time retrieval.
And CAG just loads everything it can fit up front into the model's temporary memory, and then you query against that loaded memory.
That's the key distinction, yes. Let's look at the trade-offs, comparing RAG and CAG directly based on what the sources said.
Okay, first up, knowledge base size. How much information can they handle?
RAG scales to absolutely massive databases, millions, even billions of documents, because it only needs to retrieve a small subset for any given query.
And CAG?
CAG is inherently limited by the LLM's context window size. Even with models that have very large context windows these days, hundreds of thousands of tokens, you're still probably limited to maybe a few hundred documents fitting in at once. Much, much smaller scale than a RAG.
Okay, what about accuracy?
RAG's accuracy, as we discussed, relies heavily on the quality of that retrieval step. If the retriever misses the key information, the LLM is grounded poorly, accuracy suffers.
Right.
CAG, on the other hand, guarantees the information is in the context window, assuming it fit. But its accuracy then depends on the LLM's ability to correctly identify and extract the right information from that potentially very large, dense block of text.
Which can be hard. The needle in a haystack problem.
Exactly. There's a risk of confusion or the model mixing information from different parts of that large context.
Latency. How fast are the answers?
RAG generally has higher latency per query because each question requires that dynamic retrieval step. Embed the query, search the database, fetch the text, then generate.
Right.
With CAG, once that initial potentially slow loading of the knowledge base into the cache is done, answering subsequent questions within that cached context is significantly faster, often just one forward pass through the model, lower latency per query after the initial load.
Scalability seems tied to the knowledge base size, then.
Pretty much. Our RAG is highly scalable, leveraging the scalability of the underlying vector databases. CAG's scalability is fundamentally capped by the maximum context window size of the LLM you're using.
Again, data freshness. What if my information changes a lot?
RAG handles knowledge updates relatively easily. You can incrementally add or remove documents from the vector index. New information can be available almost immediately for retrieval.
And
CAG requires recalculating and reloading the entire cached knowledge base into the model every time the data changes significantly. This can be very inefficient if your data updates frequently, kind of negating the caching benefit.
So the best approach really depends heavily on the specific situation, the use case.
Absolutely. The sources provided some great examples to highlight this exact point.
Like the IT help desk bot.
Yeah, for an IT help desk bot, answering questions from a single, maybe 200-page technical manual that's pretty static, updated infrequently.
CAG might be better.
CAG is likely the better choice there. The knowledge base is small enough to fit in a typical context window, it's static, and the benefit of lower latency for potentially rapid-fire user questions is significant.
Okay, but what about, say, a law firm research assistant? Needs to search thousands of legal cases. New ones added constantly. Needs precise citations.
Our AGI is the clear winner there, no question. The knowledge base is massive, constantly changing, far exceeding any practical context window limit for CAG.
Right.
A RAG inherently links back to the source chunks, which makes citation easy, and its ability to handle dynamic, large data sets is exactly what's needed. CAG just wouldn't scale.
And that other example, a clinical decision support system, where a doctor is asking complex questions about a specific patient, referencing their records and medical guidelines.
That scenario might be perfect for a hybrid approach.
Combining them. How?
Well, you could use our RAG first to do the heavy lifting search across the vast medical knowledge base, retrieve the specific patient's history, relevant clinical guidelines, maybe recent research papers pertinent to their condition.
Get the relevant subset of information.
Exactly. Then take that retrieved relevant subset of information and load that into a long context LLM using the CAG approach.
Cache just the relevant stuff for this specific case.
Precisely. This creates a temporary, highly performant working memory specific to that patient case. It allows for very low latency, in-depth follow-up questioning about that specific context once you've narrowed it down with our RAG.
That makes a lot of sense. Use RAID for the initial precision search across the huge data set, and then maybe CAG for lightning-fast analysis and interaction within that focused, retrieved context.
Exactly. So RAG and CAG aren't necessarily mutually exclusive. They're different strategies for augmenting LLMs, each with its own strengths and weaknesses. The optimal choice, or maybe the best combination, depends entirely on the requirements of your specific use case.
Things like the size and freshness of the data.
Latency needs, context window limits, whether you need citations, all those factors play a role.
Wow, okay. We've really covered a lot of ground here today. Real deep dive.
We certainly have. We started by acknowledging the, incredible capabilities of LLMs, but quickly confronted their real-world limitations.
Those knowledge gaps and the risk of hallucination.
Right.
And we saw how foundational prompt engineering is really the first step, helping us communicate better with the model to activate its existing abilities.
Even if it can't add genuinely new knowledge on its own.
Right. Then we spend a good chunk of time unpacking ARG Retrieval-Augmented Generation
as the core method for overcoming those knowledge gaps, bringing in that external, up-to-date, or domain-specific information.
We explored how vector databases and those vector embeddings are really the powerhouse behind that retrieval step.
Enabling that fast, semantic search even across massive, unstructured data sets.
We detailed the basic RAG workflow, the offline indexing, the online retrieval and generation, and highlighted the critical role of the retriever.
Yeah, getting that right is key.
And we saw how other prompt engineering techniques, chain of thought, ReACT, DSP, can be combined with R.
To refine how the LLM processes, reasons about, and extracts specific information from the context it's given, making it smarter about using the retrieved info.
Then we looked at how RAG itself is rapidly evolving, all those advanced techniques.
Improving the query, routing it intelligently, translating it for different databases, using smarter indexing.
And how this is leading towards agentic RAG,
where the LLM itself takes on a much more active role making decisions, evaluating the process, creating more robust and adaptable systems.
And finally, we examine that alternative strategy, Cache-Augmented Generation, CAG.
Understanding its trade-offs compared to RAG and seeing where maybe a hybrid approach makes the most sense.
Getting a handle on these techniques really feels powerful. It's the difference between using an LLM as just a general chat tool,
which is fun, but limited,
and turning it into a truly practical, reliable assistant, one that's capable of navigating vast, dynamic information sources to get you accurate answers quickly.
It's how LLMs become grounded in your reality, your specific needs.
It's incredible, really, to see how quickly these methods are advancing.
The pace is just phenomenal.
Absolutely. So maybe a final thought for everyone listening. Considering how rapidly these techniques are developing, with the LLMs becoming faster, more capable of complex reasoning and evaluation right within the workflow,
How might this combination of agentic behavior, refined prompting, and dynamic knowledge retrieval fundamentally change how you access and utilize information in the very near future?